Somewhere, right now, a machine sitting a million miles from Earth is staring at a patch of sky smaller than a grain of sand held at arm's length. It has been staring at that same tiny patch for over 100 hours, and what it found there should not exist, not according to everything we thought we knew about how the universe begins. This is the James Webb Space Telescope, and in the last 2 years, it has quietly broken almost every model astronomers had built about the early universe, the formation of planets, and what a normal solar system is even supposed to look like. Today, we're going through exactly what it found in order, starting with something so old it shouldn't be visible at all, and ending with a discovery so strange that half the astronomy community still isn't sure they believe it. Let's start at the beginning of everything. Part 1, the galaxy that broke the timeline. When astronomers pointed Webb toward a region of sky as part of a deep survey program, they were hoping to catch a glimpse of galaxies from the early universe. What they found instead was a single, faint red smudge of light that, when analyzed properly, turned out to be a fully formed galaxy that existed just 290 million years after the Big Bang. To put that in perspective, the universe is roughly 13.8 billion years old. This galaxy was already burning bright when the cosmos was less than 2% of its current age. Astronomers gave it the working name JADES GS Z14-0, and the moment its distance was confirmed, it became the most distant galaxy ever directly observed by humanity. Here is the part that actually alarmed scientists. This galaxy was not some faint, disorganized cloud of newborn stars. It was large. It was luminous. It showed signs of already containing heavier elements, the kind that are usually only produced after generations of stars have lived, died, and seeded the surrounding gas with new material. In other words, this galaxy looked like it had already been through cycles of star formation that, according to the standard model of cosmology, simply should not have had time to happen yet. Astronomer Stefano Carniani, one of the researchers involved in confirming the discovery, described the find as one that forces scientists to rethink how quickly galaxies were able to assemble themselves in the infant universe. Some researchers have started calling this broader pattern the impossible early galaxy problem, because JADES GS Z14-0 is not alone. Webb has now found dozens of galaxies from the same early era that appear far too massive, far too bright, and far too structured for their age. There are two competing explanations circulating right now. Either our understanding of how quickly matter can clump together and ignite into stars after the Big Bang is fundamentally wrong, or there is some exotic physics at play in the earliest moments of the universe that we have not accounted for at all. Neither explanation is small. Both would rewrite textbooks. Part 2, the planets that belong to no star. While one team of researchers was staring at the edge of time itself, another team turned Webb towards something much closer and found something arguably even stranger. In 2023, astronomers using Webb aimed at the Orion Nebula, a massive stellar nursery about 1/350 light-years from Earth, expecting to catalog young stars and forming planetary systems. Instead, they found roughly 40 pairs of planet-sized objects drifting freely through space, bound to absolutely nothing. No parent star, no orbit around anything at all, just wandering alone through the void in pairs. Scientists name them jumbos, short for Jupiter mass binary objects. Each one is roughly the mass of Jupiter. Each pair orbits its twin rather than any star, and by every current model of planet formation, they simply should not exist. Planets are supposed to form out of the leftover disk of gas and dust surrounding a young star. They are not supposed to form in matched gravitationally bound pairs, floating independently in open space. Astrophysicist Samuel Pearson, part of the team that identified them, said openly that current theories cannot explain how these objects formed the way they appear to have formed. There are early theories, ranging from failed star formation to violent gravitational ejection from young multi-star systems. But none of them fully explain the pairing. Something threw these worlds out into the dark, or something formed them out there in isolation to begin with, and right now nobody can say for certain which. What makes this more unsettling is the number, 40 pairs, found in a single nebula in a single survey. If that ratio holds across the galaxy, the number of starless, homeless planets wandering the Milky Way alone could be staggering, an entire hidden population of worlds that no traditional survey method was ever built to detect, because nothing about them reflects starlight, the way a normal planet does. Part 3, the atmosphere. That sparked a worldwide argument. If the first two discoveries were strange, the third one is the one that actually made global headlines because it touched the one question everyone secretly wants answered: are we alone? In September 2023, a team led by astronomer Niku Madhusudan at the University of Cambridge pointed Webb at a planet called K2-18b, a world roughly 8.6 times the mass of Earth, orbiting a red dwarf star about 124 light-years away. K2-18b sits inside what is often called a Hysian world category, a planet potentially covered by a global ocean underneath a thick, hydrogen-rich atmosphere, sitting inside its star's habitable zone. Webb's instruments detected methane and carbon dioxide in the planet's atmosphere, which on its own was already an exciting confirmation of the High-Sean hypothesis. But then came the part that made the story explode across every science outlet on the planet. The data showed a tentative signature of a molecule called dimethyl sulfide, or DMS. On Earth, this compound is produced almost exclusively by living organisms, primarily marine phytoplankton. It is, as far as we currently know, a biosignature. Madhusudan was careful in his language, stating that the detection needed to be treated with caution and required significant follow-up observation before anyone could call it confirmed. But the possibility alone was enough to dominate headlines for weeks. A potential chemical fingerprint of biological activity detected in the atmosphere of a planet over 100 light-years away. Since that initial announcement, the astronomy community has split. Some follow-up analyses have questioned the strength of the signal and argued it could be explained by non-biological chemistry instead. Others maintain the detection is real and simply needs more observing time to confirm at higher confidence. Either way, K218b has become one of the most closely watched exoplanets in existence, and Webb is scheduled for additional observation time, specifically to settle the argument one way or the other. Part 4. A black hole that should not be that old or that big. Now here is where things get genuinely uncomfortable for physicists. Webb has also been used to hunt for the earliest supermassive black holes in the universe, and in doing so, it found one, nicknamed by researchers using the internal designation GNZ11, that existed when the universe was only about 440 million years old. That alone was surprising. What was more surprising was its size. This black hole appeared to already be millions of times the mass of our sun. The problem is straightforward. Black holes are thought to grow gradually, feeding on surrounding gas and merging with other black holes over enormous stretches of time. There has simply not been enough time, according to standard models, for a black hole to grow that massive that early. It is the cosmic equivalent of finding a fully grown adult standing next to a delivery room minutes after a birth. Since that initial detection, Webb has found several more of these oversized early black holes, enough that some researchers now believe supermassive black holes may not always form the slow way, growing from small stellar remnants over billions of years. Instead, some may form directly, collapsing from massive, unstable clouds of primordial gas almost immediately after the Big Bang, skipping the smaller intermediate stages entirely. If that theory holds, it does not just change how we think about black holes. It changes how we think galaxies themselves form, because many researchers now suspect supermassive black holes may not be a byproduct of galaxy formation, but potentially one of the seeds that helped galaxies form around them in the first place. Part 5. The tool that makes all of this possible. None of these discoveries would exist without understanding what actually makes Webb different from every telescope that came before it, because the difference is not just size, it is the entire wavelength of light it was built to see. Visible light telescopes like Hubble are extraordinary at capturing what our eyes would see if they were powerful enough, sharp images of galaxies, nebulae, and stars in the colors we recognize. But visible light has a limitation. As light travels across the expanding universe, the stretching of space itself stretches the wavelength of that light along with it, shifting it further and further toward the red end of the spectrum, and eventually past what human eyes, or Hubble's instruments, can detect at all. The oldest, most distant objects in the universe are not just faint, they are quite literally invisible in ordinary visible light because their light has been stretched into the infrared by billions of years of cosmic expansion. Webb was built specifically to solve that problem. Its primary mirror, a honeycomb structure of 18 gold-coated hexagonal segments spanning 6.5 meters, was engineered to capture infrared light with a sensitivity no space telescope has ever had before. It sits nearly 1 million miles from Earth at a gravitationally stable point called the second Lagrange point, shielded behind a tennis court-sized sunshield that keeps its instruments cool to nearly minus 370 degrees Fahrenheit, cold enough that the telescope's own heat does not drown out the faint infrared signals it is trying to detect. That combination, a massive mirror, extreme cold, and infrared sensitivity, is exactly why Webb can see galaxies that existed when the universe was a few 100 million years old. Their light has been traveling toward us for over 13 billion years, stretched the entire way, and Webb is essentially the first instrument in history sensitive enough to catch it before it fades into nothing. The same infrared sensitivity is also what allows Webb to study exoplanet atmospheres in the way it did with K218b. As starlight passes through a planet's atmosphere during a transit, different molecules absorb different wavelengths of infrared light, leaving a kind of chemical fingerprint behind in the data. It is an almost absurdly delicate measurement, detecting the faint chemical signature of a planet's air from over 100 light-years away, and yet it is precise enough to spark a genuine scientific debate about the possibility of life. Part 6. why all of this fits together. Take a step back and look at these 4 discoveries side by side. A galaxy too massive and too old to exist this early. Free-floating planet pairs that defy planetary formation models. An exoplanet atmosphere carrying a possible signature of life. A black hole that grew impossibly fast in the universe's infancy. None of these were the discoveries scientists originally set out to find. Webb's early science programs were designed to confirm existing models, to measure known quantities more precisely, to fill in details around a picture astronomers already believed they understood. Instead, in survey after survey, the telescope kept returning data that didn't fit the picture at all. That pattern, finding the opposite of what a mission was designed to confirm, is historically the moment right before a major shift in scientific understanding. It happened when Vera Rubin's galaxy rotation data first hinted at dark matter in the 1970s. It happened when supernova surveys in the late 1990s first hinted the universe's expansion was speeding up rather than slowing down. Both of those moments began as small anomalies that refused to go away, and both eventually forced physics to rewrite itself. Individually, each one is a fascinating anomaly. Together, they point to something much bigger. Our models of how the universe assembles itself, from the very first galaxies, to planetary systems, to the objects that anchor entire galaxies at their centers, may be missing something fundamental. Webb was not built to confirm what we already believed. It was built with enough sensitivity to look past what we expected to find and see what was actually there. And so far, what is actually there keeps refusing to match the textbook. Webb still has years of operational life ahead of it, with enough fuel reserves that mission planners now expect it to keep observing for potentially 2 decades. Every new deep field it captures is another chance to find another galaxy that shouldn't exist yet, another planet that shouldn't be orbiting nothing, another atmosphere that might be quietly hinting at life somewhere else in the dark. So here's the real question worth sitting with. If a single telescope, in just a few years of operation, has already found evidence that galaxies formed faster than physics allows, that planets can exist without stars, that a distant ocean world might be exhaling a gas linked to living things, and that black holes may be born fully grown, what happens when it turns its mirror toward the next unexplored patch of sky? What is it going to find that we haven't even thought to ask about yet? If this kind of discovery is the kind of thing that keeps you up wondering what else is out there, make sure you're subscribed, because Webb is nowhere near finished rewriting the rulebook, and the next headline could come at any moment. Drop a comment and tell me which discovery surprised you the most: the galaxy that shouldn't exist, the planets with no star, the possible signs of life on K2-18b, or the black hole that grew too fast. And if you want to go even deeper into how astronomers are hunting for the very first light in the universe, there's another video linked right now that you need to watch.